Hello, good evening, everyone. My name is Amit. This is Gate Physics live sessions. This is week 5. We had been talking about special theory of relativity for the past 4 weeks. We'll continue the same with this week and one more week after this, and that will complete the all the problems, all the relevant problems at least, which were asked in Gate Physics in the past 10 years. We'll wait for a couple more minutes and then we'll start today's session. In the meantime, if you have any doubts or comments on the previous sessions, any
Good evening, sir.
good evening, and then in that you may ask. But I'll wait for a couple of minutes so that because some people join slightly late, so you can utilize this time. I'll mute myself. If you have, just speak up. All right.
हेलो
Yeah, Harish.
सर, आपकी वॉइस नहीं आ रही.
My voice is not there. Can anybody else confirm?
हेलो.
Hello. Am I audible?
Yes, sir, you are.
Okay.
Yes, sir.
Okay. Harish, I think there might be some trouble on your side. Just leave this session and try to join again. Okay. Let's begin now. I'm going to share my screen. Just hold on a moment.
सर, आज हम कोलिजन पढ़ने वाले हैं क्या?
Just 1 second. So Harish is asking, are we going to talk about collision today? Yes, one of the topics is collision. A couple of questions before that on energy conservation. So today's class will more or less focus on the two very basic conservations that we talk about: the conservation of momentum and conservation of energy. So today we'll be focusing on that. So let me begin. Is my screen visible? Can anyone confirm?
Yes, sir.
Okay. And I hope my voice is also audible. So this is week 5. My name is Amit. These are Gate Physics live sessions hosted by NPTEL. I'm a PhD scholar at Indian Institute of Science, Bengaluru. So we are talking about special theory of relativity. This talks about relation between space and time. The way we denote space is xyz, and time we denote it by t. So this is the nomenclature that we had been following. Semicolon t. Just remember this. Following, what's special about it, that we are neglecting the gravity. So, and the twin concepts that are involved in this special theory of relativity are as follows: the laws of physics remain invariant, means the laws of physics will not change. What laws of physics we are talking about? Conservation of momentum, conservation of charge, and conservation of energy, as we see today. What do you mean by inertial frames? Inertial frames are those frames in which have zero acceleration. This means velocity is not a function of time. So that means velocity is zero, that means at rest, or some constant velocity in any of the three directions x, y, z. And the second and important thing is that speed of light is same for all frames. So speed of light will remain c irrespective where you are traveling. Like, these terms keep on coming over and over again, and I'll again, before beginning to solve the problems, I'll go through these terms. So first is observer. We already know what is an inertial frame. What is an observer? So this is a frame. This we usually call the rest frame or the lap frame, and this is the frame S, and here is an observer O sitting at the origin. So this observer will observe certain things. And also, as I've told, inertial frame can be moving also. So this is a frame S prime which is moving at a constant velocity v. Note that v is a constant in positive x direction, and another observer is sitting at O prime. So O and O prime are two observers. What they'll do, they will observe some things called events. What is an event? Event can be anything. Like clapping or bursting of a bubble, any visual, audio, anything of significance is an event, and we denote it by like this coordinate x1, y1, z1, t1. Similarly, the same event will have O prime will also observe the same event. So we denote by prime here. So this will be x1 prime, y1 prime, z1 prime, semicolon, t1 prime. Similarly, they can be even q, which will be like 2, 2, 2, and so on. Similarly, q prime will be here. Now the important thing here is that the space-time interval is a mathematical quantity that we define, and it remains invariant across different inertial frames. This means if you calculate this quantity delta s in this frame and in this frame S prime frame, their square will be the same. This is just like that we see in the distance that we see in a normal rectilinear system. So this is the mathematical expression for delta S square. So C delta t, this is called the time interval. Time, you can see the time term is there. Delta t, what is? T2 minus T1. So I told you there is x2, y2, z2 and t2 here, right? So difference between those is delta t, delta x, delta y, delta z respectively, and this is called the space interval. Space interval. Together, by subtracting the space interval from the time interval, we get space-time interval, which is denoted by delta s. Here we are calculating delta s squared, and yeah. So based on this invariance of space-time, we now our objective here is that excuse me. Yeah, our objective here would be to how to convert like x1 prime into x1 and vice versa. So that we do through something called transformations. But first, let's see a non-relativistic system. What do you mean by non-relativistic? That velocity, this v, is less than c. So we know in that case that t prime, which is measured here, like we saw p, right? x1, y1, z1, t1. Similarly, there was p, sorry, this was p prime, x1 prime, all primed, and this was p, x1, y1, z1, t1. So whatever time is measured by O here for this event p, these will be the same, and because this is traveling in x direction, so x prime will be shifted by vt factor. Y and z will remain the same because there is no motion in y and z direction. However, in case of a special theory of relativity, where we are talking about speeds very close to light, this concept comes into picture, and we can derive that the same formulae transform to this. So this is non-relativistic, you can see here. This is relativistic. This means v is comparable to c, obviously not greater than c. Let's say 0.1 c, 0.2 c, 0.6 c. So however, t prime and x prime and so on are given by this factor, where v is the velocity of the s prime frame with respect to the rest frame. This was the rest frame, and yeah, t is the time here, and all other things are self-explanatory. C is the speed of light. Similarly, what we need to do, sometime we know the coordinates here, the space-time coordinates here, and we need to know the coordinates here, and we know the coordinates, these are known, right? So then we can use the inverse Lorentz transformation, and we can get the value of t and x in term if t prime x prime are given. These are the expressions that again kindly make sure this is the rest frame, by the way, and this again v is constant here. These are non-accelerating frames. Similarly, since we know that velocity is nothing but, for instance, vx will be nothing but dx over dt, or we can say delta x over delta t for simplification. We saw that we derived these expressions ux prime, uy prime, uz prime if ux, uy, uz were given. Similarly, if you want to know the inverse side, that is ux prime is given and you need to know ux, you can use this formula. Again, this is the rest frame, and this is the moving frame s prime at a constant velocity v in positive x direction. Then we saw some practical impacts like time dilation and length contraction. So up until this point of time, we have discussed in last class. Yeah, sorry. Yeah, so last time I did this problem, if you remember, that there's a length contraction problem, but I did a calculation mistake, so I just want to repeat it. So how do we solve these problems? Can you see the problem? Just confirm.
Yes, sir.
Okay, so this was the problem that a rod of proper length L0. We saw this term proper last time. What does proper mean? Proper means in frame of object, in frame of reference of object, frame of reference of object. So you have to be sitting on the object, and then you can measure proper length and proper time. So we were given proper length L0 is oriented to parallel x-axis. I'll solve this, but before solving the problem, we check, there are a few pre-checks that we first note that all the frames are inertial. So first, usually frame is a rest frame, which is naturally inertial. Second frame is the moving frame, right? What is the moving frame here? So moving frame, you can see so there are, rest frame is S frame, so there is a moving frame. So observer is moving along the x-axis with speed c by 2. So this is our moving frame. We call this S prime, which is moving at c by 2 in positive x-axis. It's given, right? And since it's a constant speed, so this means the moving frame is also inertial. So this is also inertial. The rest frame is naturally inertial. Next is moving frame. What is the speed and direction? So the speed of moving frame is given as c by 2. So we know v value is given at c by 2 I cap. What is the direction? Direction is x, and hence this I cap, you can see it's given positive x direction. Next is number of dimensions. Number of dimensions is how many of x, y, and z do you need to consider. And notice that the question is silent about any other axis except x-axis. So this problem becomes a 1D problem, and hence a relatively simple problem. Now I'll just draw the diagram that what's being talked about. So it's a rod of proper length L0 oriented parallel to x-axis, moves with 2c by 3 along the x-axis in S frame. So this is our S frame, and there is a rod sitting here, right? But this rod is not stationary, it's moving at a speed of 2c by 3 in this direction, right? And there is another frame S prime here, and this S prime is moving at a speed c by 2 with respect to the S frame, the rest frame. This is the rest frame, right? So this is what we knew, right? I see the speed of observer is moving at us along the x-axis at speed c by 2 with respect to S frame. This is what I have drawn here. So this is the observer we are talking about here. The length of rod as measured by observer. So we need to find the length of rod in this frame. So here we need to find the length of rod, right? So what we do know is that, yeah.
सर एक सर जो प्रॉपर लेंथ एल नोट आप बोल रहे हो,
Yeah,
ये मतलब कौन सी फ्रेम में दिखेगी?
that's what I told you, that the proper length. So Harish is saying ki in which frame do we see the proper length? As I told before, the proper length is seen in the frame of reference of the object. So here, for instance, in this case, I must draw another frame. I call this frame S rod. So in this frame, we'll be moving at 2c by 3 with respect to rest frame, and here the rod will appear at rest. So here you will see ux double prime, I'm denoting it's 0, right? Here also it's the rod. Here it's moving at some speed ux prime. We don't know that. And here the length would be L prime. Here the length is L0. So in this frame, this is called the proper length because rod is at rest here. You see ux double prime equal to 0. So rod is at rest here, and hence the length measured by an observer sitting at here, somewhere here, will be L0. So now moving forward, in order to calculate the length contraction here, right? So what we need to know is that we know the length contraction. So I am just reproducing this formula. So I am writing length in S prime will be equal to proper length divided by gamma. This is and we need to know the L prime. So length in S prime is proper length by gamma. Proper length we know is given in the question as L0 gamma. Now I'll writing the value of gamma here. So gamma would be, we know the formula for gamma is 1 minus v square over c square. What is the value of v here? V is the v relative, that is velocity of object with respect to frame over c square. So this means velocity of object with which frame are we talking about? We are talking about this frame here. So let's say this is gamma prime. Okay, gamma prime. So gamma prime would be 1 upon velocity of object with respect to frame S prime. So in S prime, what is the velocity of the object? We know the velocity of object. The way convention we use is ux prime. So I can write is 1 minus ux prime whole squared over c squared. How do I calculate ux prime? Ux prime I can calculate using this formula. Uc is given 2c by 3 minus v is given as c by 2 over 1 minus 2c by 3 into c by 2 into 1 over c square. So that is the expression that I have gotten. Now what I'll do is I'll just simplify this. So this will be by 6, 4 minus 3, this will be c by 6. This would be 1 minus 2 and 2 gets cancelled, c square gets cancelled, 1 minus 1 by 3. 1 minus 1 by 3. So this will be c by 6 upon 2 by 3. So this goes like this. This is coming out to be c by 4. So ux prime is c by 4. I'll simply put this value here, 1 minus c by 4 whole squared over c square. So this will be 4 upon root 15. Okay, now I need my calculator. So let's put this here. So this will be root 15 L0 by 4, and square root 15 is 3.87 divided by 4. So this is coming out to be 0.968 L0. So proper length in S prime is coming out to be 0.968 L0. So 0.968, so 0.968 L0 was our answer, which is the closest option is option D. So last time the mistake that I had made was there was a typo in this formula here. So the minus was missing, copy paste error on my side. So that's why I did this again. And the second reason for doing this is I just needed to again make sure that proper length. Somebody asked just now, when do we measure proper? Proper is measured in the frame of reference of the object. So object has to be at rest. You see ux double prime equal to 0. So there is some third arbitrary frame S rod in which we are measuring the length L0, and rest all is straightforward. We know the formula that length in any other frame equal to proper length divided by gamma. This is L0 divided by, here I am noting gamma is gamma prime because the other frame is this one. So this is L, we need to know L prime. I just calculate the value of gamma prime. The key thing here was, what is this velocity? This velocity is velocity of object with respect to frame. Here we are interested in the frame S prime. Hence we did ux prime whole squared, and I calculated ux prime using this formula, the very straightforward formula that we had seen 1 or 2 sessions earlier. And the rest is very simple mathematics. So that's that. I'll pause a bit here so that if you need any other clarifications or comments regarding the length contraction or time dilation, just feel free to ask. So this was the topic that we were doing earlier. So that's that. I'll pause a bit and then I'll move forward. If you have any comments, please speak. All right, let me move forward now. Okay. So last class also we had started about the expressions of mass, momentum, and energy. So this is my rest frame as usual, or left frame denoted by capital letter S. And so let's say there is an object here. Its rest mass is m0. Now the key, you have to be very careful about these terms. What do we mean by rest? This means this object is not moving right now. So if this object is at rest, its mass is m0. However, if this object starts moving with some velocity, then its mass changes. It becomes relativistic mass, and it's denoted by gamma m0. The gamma factor again remain the same, that 1 minus v square over c square. What is this velocity v? This velocity is velocity, again v remains the same, velocity of object with respect to frame. Which frame are we interested in here? S. So with respect to frame S. So that's how this is the gamma here. Similarly, if we know mass, we know from our high school physics that momentum is mass times velocity. The question is, in case of relativistic momentum,
Hello.
which moment?
Hello.
Yeah.
हेलो सर, ये v वेलोसिटी ऑफ ऑब्जेक्ट विद रेस्पेक्ट टू s प्राइम फ्रेम होना चाहिए सर.
There is no S. So Harish is that you? Yeah. No, wait. Yeah, Harish. So Harish is saying that the velocity v here should be with respect to S prime frame. There is no S prime frame here. There is only one frame. You know that you can. So I have only one frame, rest frame here, and here let's say I see this object moving with some velocity. Let me stick to the convention, moving with velocity ux. So I'll call this like this, ux square by c square. There's no S prime frame here. If there is another frame S prime which is moving, we'll see in our questions, then again this changes. The important thing to remember is that this velocity is nothing but the velocity of object with respect to frame we are interested in. So here we are interested only with respect to frame S. Note, I have only drawn one frame S. If there is any other frame, yeah, this will change accordingly. This is not necessarily, So what you might get confused is that earlier this used to be the velocity of the frame v. No, this is supposed to be the velocity of any object. This is a general thing. In the previous questions which we have talked about, there were 2 frames. Here there is only 1 frame. But this concept is generalized. Right, moving forward, so we have relativistic momentum. Momentum we know is mass times velocity. We know that. Mass times velocity. So here, in case of relativistic momentum, what is the mass and what is the velocity? It's fairly simple. The mass would be relativistic mass, and velocity would be relativistic velocity. So ux in this case. Note that I'm only considering only the x dimension. If there are y dimensions, then this formula will accordingly change. So ux plus uy plus uz, and the vectors will come in. But this is a very simplistic picture, one-dimensional picture. Once we have defined momentum, similarly we can define energies. So again, note the word rest. This means the object is not moving. Its velocity is given by m naught c square. If it is moving, it is given by this factor, pc whole square plus e naught square. Note this is the rest mass energy, rest energy. Sorry, not rest mass energy, rest energy. And this is due to this is a momentum factor that comes. However, if it's asked what is the kinetic energy, it would be the total energy, relativistic energy E minus E naught. Okay, I repeat, the kinetic energy, relativistic kinetic energy will be total energy E minus rest energy E naught. This is the expression that we will be using. Excuse me. Okay, now so I'll just clear the ink here. So these are the formula that we had talked about, right? And this expression that you see, E equal to mc square, is the famous expression. E naught equal to m naught c square rather. And similarly, you can also say that this is equal to mc square, where m is what? Relativistic mass. So all the things just get changed. So E equal to mc square is a general expression. If it's at rest, we add this subscript 0 here. So E naught equal to m naught c square. So you can also say mass energy equivalence is E equal to mc square. This is the total energy, mind you. This is total energy. Kinetic energy would be E minus E naught. This is rest energy. So this is very straightforward. I mean, there is nothing to explain here. I'll directly jump into the questions so that we can have more clarity about it, right? And these questions will be very straightforward, very simple. If you just know the formula, you can directly put it and just understand the problem. So this is a problem from 2016, in which it states that kinetic energy of a particle of rest mass m naught. So as always, I'll draw my frame of reference. This is my rest frame of reference, S. My observer is sitting here at O, and there is a particle here, right? I'm calling this particle P. Okay, the kinetic energy of this is some particle, right? It has some kinetic energy. This means it is moving. Okay, so I'll assume it's moving with some velocity ux. Okay, and its kinetic energy is equal to rest mass energy. Okay, so it's given that kinetic energy is equal to rest mass energy. Somebody is not muted. Can you please mute yourself? Thank you. Right, so it's given kinetic energy of this particle P, which is moving at some velocity ux, is equal to its rest mass energy, and its momentum in units of m naught c is. So we need to find out what is the momentum. So we need to find what is the momentum in units of m naught c. This means there will be some factor. We'll just note that. This is the problem statement, right? As always, we'll do some pre-checks. So what pre-checks are? All the frames inertial. So how many frames are there? There's only one frame here, which is rest frame. And since this is at rest, this means it is inertial. So this is correct. There's no S prime frame in this case. If there were any S prime frame, which we'll see in other questions, then we'll introduce it. But here there is only one frame. So next question is, what is the in case of moving frame, what is the speed and direction? This is not applicable in this case, because there is literally only one frame which is at rest, right? How many dimensions? The question is silent on the dimensions. For simpler understanding, I'm considering only the x dimension. So I'll say one dimension, which is x, right? These are the formula that we can use. So what's given is that kinetic energy is equal to rest mass energy. So I'll do that. Kinetic energy formula is E minus E naught. So I'll write it here. E minus E naught equal to rest mass energy. Rest mass energy is E naught. Okay. So this will give me E equal to twice of E naught. Okay. Now I'll write the expression for E and E naught. So E expression is PC whole squared plus E naught squared equal to 2 E naught. If I take square on both sides, this will become PC whole squared plus E naught square. 2 E naught squared is 4 E naught squared, right? Taking the all the terms on the, sorry, so I'll write this P square C square equal to 3 E naught square. I know the value of E naught is m naught times C square, so rest mass is given as m naught, so I can write this m naught C square whole squared. So here it will come P square C square equal to 3 m naught squared C to the power 4, and I'm writing here, so this will become P square will come equal to 3 m naught square C square. Now taking the square root on both sides and interested only in the magnitude, so it will become root 3 m naught C, root 3 m naught C. So the momentum is coming out to be root 3 m naught C, and we need to find the momentum in units of m naught C. So this is the, you can see this is the unit, right? So what is the coefficient of this? Root 3. So I'll write this at root 3. Oh, sorry, I forgot. This is up to 2 decimal places. So root 3 is 1.732, and since we are required to find to 2 decimal places, I've always told you this is important. Sometimes you, even though you solve correctly, you might not be awarded marks. For instance, if you write 1.732, this will be an incorrect answer and you'll get 0 marks for this. 2 decimal places, it's 1.73, so this will not be root 3. The answer would be 1.73. so that was a complete problem. I'll just summarize it once more, that what was the problem and how we solved it. So it's a straightforward thing in which we were given that some particle P in this case is moving with some velocity ux. I assumed only in the x direction. This is a very general, this is a safe thing to do. That's all I can say. And Ke was kinetic energy. Relativistic, I should say this, the relativistic kinetic energy is equal to rest mass energy. So I just put the formula over here, arrange the terms, and obtain the value of this expression P naught square, P square equal to 3 m naught square C square. Took the square root, and we are interested only in the magnitude of the momentum. Hence it will come out to be root 3 times m naught C, and we are required to find in terms of units of m naught C. So this will come out to be root 3. Rounding off is 1.73. So this is a very straightforward, purely formula based question. So these are some of the, and in this case we saw that it has only one frame, so that the question of s prime does not arise. If the s prime were there, then all the velocities here will become the relative velocities with respect to that frame. So all, you know that ux, what was ux? Ux is velocity of P with respect to s. This is a key thing here. This is an assumption here. So that's all. That's the problem. I'll pause for a minute here, and if you need some clarifications, if you have some comments, please speak up.
सर हेलो
Yeah.
सर, इस क्वेश्चन को हम मतलब हमें यहाँ से E इक्वल टू 2 ई नोट लिखा आपने, ठीक है, और यहाँ से मैं क्लियर देख पा रहा हूँ यहाँ पे गामा इक्वल टू 2 मिल रहा है, ठीक है, जिसके कोरोस्पोंड हमें ux इक्वल टू रूट 3/2c मिल रहा है, ठीक है. तो इसको हम p इक्वल टू
No.
एमवी वाले फॉर्मूले में रख कर भी कर सकते हैं ना.
हाँ, okay. So Harish, I'll translate what you are saying to English, and I'll also request you to, if possible, just try it, because there are some other people who might not be who might not understand languages other than English. So if possible, otherwise I'll just translate. So what he's saying is that since E equal to 2 E naught, and we know that this is equal to gamma m naught C square. So we can directly say that gamma equal to 2 here. So if gamma equal to 2, we can calculate the velocity, because we know that the gamma is 1 minus ux square over c square. So we can get ux from here. You're correct. You can get ux from here. You will get ux, but remember the formula of momentum is mass times speed, right? So ux you can get. How will you get mass? This is again gamma m naught ux. So you have the value of gamma. So this is 2 m naught, and you calculate the value of ux from here. You can do that. Why I did not do this approach? Because it has more calculations. Okay. And just a general piece of advice, that the fewer calculations you have in your problems, the chances of error decrease. So here what you have to do, you have to calculate first ux, then you have to multiply the terms. So you have two steps of calculations. Here there's only a single unified step. So that's why the chances of error decrease, but conceptually you're correct. You can do that. You can calculate the value of u speed and from gamma you can get the speed, and if once you know the speed, you can simply put p equal to mass times velocity, relativistic mass times velocity, and you can get your expression. Yeah, you can do that. Right, any other comments? Anyone? All right, let's move forward now. So this is again, now the last question had only one particle. Here there are more than one particle. You can see two particles it's talking about. So we'll see how to approach these problems, but this is a very how should I say this, you must have done some problems regarding the collision in maybe secondary 11th 12th, or maybe even in high school. So this is again the concepts are very similar. Remember, we had talked about that the laws of physics remain invariant, like conservation of momentum and conservation of energy. Bear that in mind, and we'll try to solve this problem, right? So it says that two particles each of rest mass m. Okay, so I'll say there's a particle 1 with rest mass m. So what I'm doing is, I'm just for the sake of simplicity, I'm going to say it m naught, because then all the formula will be changed. So just assume that everything in place of m, it's m naught, right? And there's another particle p2 which again has rest mass m naught. They collide head on. Okay, so I was wrong in this case. So p2 is not here, p2 is somewhere here, and they collide head on. This means p1 is coming this side, p2 is coming this side. Of course this happening in a frame S, which is at a rest frame or the laboratory frame. So p1 is moving to the right and p2 is moving to the left, and we are given the velocity. So I can say the ux is given. Similarly ux2 is given. Ux1 and ux2 are given as 0.6 c, right? What happens is, this is before collision. After collision, what happens is they stick together. So let's call this particle p, and let's call its mass is capital M. Rest mass is capital M naught. Okay, so we'll call this M naught to determine the rest mass, this entity. This is again is frame S, and let's say this, the velocity of this big particle is ux in positive x direction. Right, as always, some pre-checks. Inertial frames, there's only one frame, rest frame. So yes, all the frames are inertial. What about moving frames? There are no moving frames, so this is not applicable. Number of dimensions, question is silent on the number of dimensions, so it's safe to say it's one dimensional picture, which means we are considering only the x-axis. By x-axis, all the formula that we have seen are in x-axis, right? So to solve this problem, now you see, in case of problems related to collisions, or this can be, we'll see later, this will be decay also. So there are two-step process. First is, what we'll try to do is, we'll try to do the conservation of momentum. Note that we notice that laws of physics remain invariant in all the frames, right? So I'll try to calculate the momentum before collision, right? These are coming, this is p1, this is p2. Let's calculate the total momentum before collision. Okay, so so this is the formula. So total momentum p would be p1 plus p2. Note, momentum is a vector quantity. So what is the p1? P1 would be m1 times u1, plus m2 times u2, where m1 and m2 are relativistic mass. Please note that, right? So m1 would be gamma times m naught. Note, both of them have rest mass m naught. Both of them have rest mass m naught. It will be gamma m naught times u1 prime. So what's the value of u1 prime? It's 0.6 c. It was given in the problem, I cap, plus m2 will again be gamma times rest mass. Let's say gamma 1, gamma 2. What's the rest mass? Its rest mass is also m naught, given in the problem, and its velocity is minus 0.6 c I cap. Note, negative x direction. This is frame S, this is x-axis, right? So we get this. Now we just need to find gamma 1 and gamma 2. That's very straightforward. So gamma 1 would be 1 minus ux1 whole square over c square. Why ux1 c square? I told you, velocity of object, in this case object is p1 with respect to frame, with respect to s. Okay, so ux1, so this will come out to be 1 minus 0.6 c square over 0.6 square c square, sorry. So this will come out to be 1 minus root 0.64. This will come out to be 0.8, right? So 0.8 is 5 by 4. Okay, so yeah, so gamma 1 will come out of this. Let's calculate gamma 2. gamma 2 is 1 minus ux2 square over c square. This will come out to be 1 minus 0.6 c squared over c square. Again this will, because minus squared will become the same, this will also come out to be 1 over 0.8, hence 1 by 4. So gamma 1 equal to gamma 2, you can say gamma 1 equal to gamma 2 equal to 5 by 4. So I can take gamma m naught common, so this will come out to be, I'm just denoting this as gamma m naught, this will be 0.6 c I cap minus 0.6 c I cap, this will come out to be 0. So we notice that before the collision the initial momentum is 0. That's what we call the initial momentum. So this is the initial momentum. What's the final momentum? What's the final after collision? What happens? This is the frame S. Here I have just one particle P with mass capital M naught, rest mass capital M naught, and we assume it's moving with velocity ux, right? So let's calculate the momentum of this particle. So this particle, the momentum would be momentum I'm denoting as capital P, so this would be gamma m naught, this is the, I should say, m times ux. M I can write as gamma m naught times ux. This should be equal to 0, right? Because initial momentum was 0. Conservation of momentum says initial momentum should be equal to final momentum. This is conservation of momentum, right? So 0 should become equal to gamma m naught times ux. We know gamma cannot be 0, right? So this goes out of the picture. M naught cannot be, m naught is not 0. So only thing that remains is ux equal to 0. This means this mass after collision P1 and P2 will stick together, and the entity which remains, that is particle P of mass m naught, will remain at rest. So this is a very important observation. So sometimes a question can be asked, what is the velocity of the final object? So this is the way you do it using the conservation of momentum, and we see that P is at rest. So this is the picture where we talked about conservation of momentum. In the next picture we talked about conservation of energy. We are assuming it's an isolated system, means in the universe only there are two objects, P1 and P2, and finally the P object. So again this is the initial picture, this first mass, this is second mass, P1 and P2. I'll calculate the total energy. So total energy would be E1 plus E2. These are scalar quantities, right? So it will be PC whole square plus E naught square, right? So I can write is P1C whole square plus E naught square, this is the first term, plus P2C whole squared plus E naught square. Note that since for both of them rest mass is the same, so rest energy will also be the same, okay? And so now I need to calculate P1 and P2, right? So P1 would be gamma times m naught into U1, right? This will come out to be gamma m naught 0.6 c I cap. P2 would be gamma m naught U2. This will come out to be gamma m naught minus 0.6 c I cap. But when you do a square, note there's a square here, so this will be the same. So hence this will become twice of, so I can write P1 equal to P2, magnitude of P1 equal to magnitude of P2 equal to P. So I can write this PC whole square plus E naught squared. Okay, so if I try to, oh no, correct. So this is PC square plus E naught square. Now note that this term is nothing but E1, the total energy of E1. Look at this formula. So if I put it like this, you can see that this is 2 times E1, right? This means 2 times gamma m naught times E naught. Sorry, gamma times E naught. Gamma times E naught. So it will be 2 gamma E naught. This is the initial energy. Let's calculate the final energy. This is of the particle P. So I calculate energy of particle P would be, this would be gamma capital M naught c squared. Since this is at rest, so gamma will come out to be 1. This will come out to be m naught c square. And conservation of energy says that these two terms should be equal. E should be equal to EP. Initial energy E, which is 2 times the value of gamma we calculated in the last slide, 5 by 4. So 2 into 5 by 4 into E naught this should be equal to m naught times c square. The value of E naught is, so this is 2 into 5 by 4. The value of E naught is m naught c squared. M naught c squared. This is capital M naught c squared. C square get cancelled. This gets cancelled. So I get m naught equal to 5 by 2 small m naught. This is the thing that we get, and 5 by 2 m naught. Yeah, note that I said that consider them all to be m naught. Right, so we get 5 by 2 m naught. So C is the correct answer here. Right, I'll pause a bit here. I'll repeat. First I'll just repeat what I had done just now. So what we were given was that there were two particles, each of rest mass m naught. So this is particle P1, this is particle P2. They were traveling like this with same speed, so 0.6 c and 0.6 c. Naturally they will collide, which is given, and they will create another mass, let's say capital P, and I assume that is moving at the velocity of ux. This is all happening in rest frame, S frame. This is before, this is after. Right, and I noticed that so first I did because there's a collision involved, so I did the conservation of momentum. There's no external force, so momentum must remain conserved. So I did that, and I find out that initial momentum is 0. This is just a very simple algebra. We found out the initial momentum is 0. Since the momentum has to be conserved, we also find out that the final entity also will have to be at rest, because otherwise it will violate conservation of momentum. After that, we found out we put the conservation of energy picture. So I calculated total energy, which is E1 plus E2, or I should have actually done this gamma E naught plus gamma E naught. This would have been much simpler. So this is 2 gamma E naught, and gamma we calculated in the last slide is 5 by 4. So 2 into 5 by 4 into E naught. So this is 5 by 2 m naught c squared. So that's what we did here, 2 gamma E naught. And energy has to be conserved, so this has to be equal to the energy of this particle. So this particle P is at rest, so gamma will come out to be 1. So energy of this particle will be m naught, capital M naught c squared. Equated the two and found out the capital M naught is 2.5 or 5 by 2 times small m naught, which is our option C here. So just to reiterate, conservation of momentum and then conservation of energy. If you have the formula, just be patient, take your time, plug everything in, and you'll solve the problem. There's nothing very difficult here that we are talking about. Just very simple algebra here. Right, I'll pause here and I'll wait for you to ask your questions if you have any doubts regarding this problem.
No doubt, sir.
Anybody else? If no, then we can move forward. Okay. Right, moving forward. So just now we saw the problem. In the previous problem there were two particles coming together, right, and we saw that the final entity was at rest, ux equal to 0. This is the reverse picture of this. So in previous problem we went from here to here. In this problem we are going from here to here. Note the language. Particle with rest mass m. So we saw the particle with rest mass m naught, right? This m naught is at rest. So it was at rest in the final question. This is the initial picture. It's at rest and it decays, right? So when it decays into two particles of equal rest masses here, these particles also have equal mass, small m naught, right? Of equal rest mass is 3 by 10 m, which move along the z-axis. Now this is interesting. So all this is not happening along the x-axis. This is happening along the z-axis. And we are required to find the velocities of these two particles, the after picture, right? As always, some pre-checks. So everything is, as I told you, everything is happening is in S frame. So this is the initial picture on your right, the final picture is on your left. So initial frames, yes, all frames, and there's only one frame which is rest, so is inertial. What about moving frame? There are no moving frames, and in fact all the other particles are at constant velocity. So we can directly apply all the formula that we have seen here. Number of dimension, it's one dimension. Interestingly, this is z-axis. You see, z-axis. Now all the formula that we have derived are for x-axis, right? But note that since it's a 1D problem, if in all my formula if I replace x by z, the discussion will not change. Discussion will remain the same. So I'll just simply pretend it's written x-axis here, and I'll simply do x cap, x cap, x cap, x cap, x cap. I've changed the problem because I'm comfortable with x direction, hence I do that. If there were two things like x and y or x and z, then I could not have done this, right? So just this is the only thing that I want to point out in this question. Now again we'll do the same that we had like we had done earlier. First we apply the conservation of momentum. So this is the initial picture. This particle P has mass m naught with ux equal to 0. This is the final picture where two particles are there. So let's say this is first particle with P1 with mass rest mass m naught, and let's say velocity is u1, and there's another particle P2 with rest mass m naught, and let's say its velocity is u2. Both velocities are in positive x direction, frame s, right? So initial momentum I can write P equal to m times u. U is 0, we can see, so this will come out to be 0. Sorry, this is capital P, so this will come out to be 0. Fine, let's calculate the final momentum. So final momentum would be, so I can see final momentum small p would be small p1 plus p2. So this would be m1 u1 vector plus m2 u2 vector using this formula. This is a relativistic mass, so I can write gamma rest mass for both is m naught. So it's gamma m naught u1 plus gamma m naught u2. So gamma m naught I can take common, this will be u1 plus u2, right? And conservation of momentum says that initial momentum, which is capital P, should be equal to final momentum, which is small p. 0 should be equal to gamma m naught u1 vector plus u2 vector. These cannot be 0. This means u1 vector has to be opposite to u2 vector, or just for the sake of simplicity I'll say u2 vector has to be in opposite direction to u1 vector, same magnitude but opposite direction. This means I just have to, so I can say that, yeah, so this is what we found out, this is in opposite direction. And let's say the magnitude of u2 is equal to magnitude of u1 is equal to u. Just for the sake of simplicity I'm doing this. Okay, now we'll now do the conservation of energy just like we did in the last problem. So this is the particle P, capital P with rest mass m naught. So energy would be, what's energy? M, capital M naught c square. This is at rest, so its energy would be m naught c square. In this picture, so this is moving at u1 in this direction, this is moving at u2 in this direction, this is P1, this is P2. So here the total energy would be relativistic energy E1 plus relativistic energy E2. This would be gamma m naught c squared plus gamma 1 m naught c squared plus gamma 2 m naught c squared, right? So I'll take m naught c squared, m naught is the same, hence this will be gamma 1 plus gamma 2. Now again gamma 1 is nothing but 1 over 1 minus u1 square over c square, and gamma 2 would be 1 minus u2 square over c squared. Okay, so this is what we found out, and u1 was equal to u2 equal to u, so I can say gamma 1 equal to gamma 2 equal to 1 minus u square over c square. So I'll simply so this will come out to be 2 gamma m naught c squared. Yeah, we are required to find the velocities. Okay, so this initial energy E initial should be equal to E final. So EI should be equal to EF. This means m naught c squared should be equal to 2 gamma m naught c squared. C square gets cancelled, and m naught is given as 3 by 10 m. So this is m naught 2 gamma 3 by 10 m naught. M naught gets cancelled, so we get gamma equal to 5 by 3. Gamma equal to 5 by 3. You put this equal to 5 by 3, and this will come out to be 0.6 equal to 1 minus u square over c square. This means u will come out to be 0.8 c. So u is coming out to be 0.8 c, and we know that u1, so u1 magnitude will also, I'll do in the next slide. We found out u equal to 0.8 c. What was u? We saw that u1, we took it equal to u2, and it's come out to be u. So the magnitude of both these velocities will be 0.8 c. So let's see the options. So this cannot be correct because it's 0.6 c here. This cannot be correct. One of the options is 0.6 c. So velocity had to be 0.8 c. So either A or B. And we also noticed that u1 was in opposite to u2. So here the direction is the same. This cannot be the answer. This is the answer. U1 equal to minus U2 equal to 0.8 C, and I notice everything we solved in one dimension, so instead of Z you can just say X. It's for general thing. So this is a question which is exactly similar to that, just the picture has been reversed. There the two particles are colliding and sticking together to come at rest. Here a particle was at rest and it decayed into two particles. So analysis remained exactly the same. We first balanced the momentum, then the energy, and we found out in this case we were required the velocity. In that question we were required to find out the mass. So that's all. It's a
सर
very
इन दोनों क्वेश्चन में
yeah, go ahead.
सर इन दोनों क्वेश्चन में एक डिफरेंस है, मतलब इसमें जो पिछले वाले क्वेश्चन में आपने एनर्जी का फॉर्मूला उसमें ये लगाया था E इक्वल टू पी सी स्क्वायर प्लस एम डॉट सी स्क्वायर वाला, और इसमें जस्ट सिंपल फॉर्मूला लगाया गामा एम डॉट सी स्क्वायर वाला.
No. So one more thing. So Harish is saying that there's a difference. He's saying that my comments are incomplete in the sense that in the previous question I had used a different formula for E naught than this. It's partially correct, but what I mean is when the questions are similar is that they're similar in flow. So you first balance the momentum, then balance the energy. So you can arrive at the final answer in any way. So my as I've told earlier also, my aim here is not to solve the question. By solving the questions, I'm just trying to tell you how I solve my questions and what best practices I have, not just me, for my colleagues, for other people who have cleared the exams and who have not cleared the exams, they have their approach. So whatever good things I have learned from others, especially, I just try to put it in one question and try to convey it to you through this medium. So what you are saying is yeah. So even though I had used this formula, but in the summary I did this also. So you can use either formula. See, the approach will not change, the answer will not change. Sorry, approach can change, the answer will not change, and that's what I'm trying to convey here. Okay, yeah. So that's that. What's the time? Oh, we have some time. I think I can. You have any other comments or questions on this, or we can just quickly try to squeeze in one more problem. All
No,
right.
sir.
Okay, let's go ahead then. For the final problem, I don't think I'll be able to finish this, but at least let me introduce the problem. So,
एक्सक्यूज मी सर.
yeah.
सर आप मतलब ज्यादा टाइम नहीं लोगे क्या आज?
No, the thing is, see, so he's asking that whether I stay longer, like above 8. I don't have a problem staying above 8. The thing is that when we say this
सर
session,
मैंने आपको कुछ क्वेश्चन सेंड किए थे.
I know, Harish, I know. Just let me complete my argument and then I'll address your concern. So the thing is that when we say that we are meeting from 7 to 8, it's not just my time, right? I assume wherever you're sitting, in your homes, in your hostel rooms, wherever you are, right, you have a commit. I assume that my aim is to start at 7. I start at 7:04 or 7:05. I know that's a deliberate thing because some people join late and I myself can. So I try to start from 7:05 and I try to finish at 8 because other people also have commitments. I can stay up to 8:15 or even longer. I don't have that problem, but I try to convey whatever I want to convey in that 1 hour because you might have other commitments also, the people who are joining in this session. So that's the idea. So that's why I try to as much as possible try to stick to the deadline. Obviously I feel free to leave anytime you want, anyone who wants to, right? So this is again a problem. So you see, first we talked about problem on collision, and then we talked a problem on decay, and some people of you might have noticed they are the same except it's happening in reverse. In collision, two or more things come together and they may or may not stick. In this case they were sticking in the problem we saw. In decay, usually there is one entity which just decays into two or more than two entities. So here again this is a decay. So you can see what says that particle of rest mass m. So there's a particle here somewhere. Let's draw it here. This fellow, this particle p is happily moving along the x-axis in positive x direction. So this is the positive x direction. It decays into two photons, gamma 1 and gamma 2. So this is the first photon, this is the second photon, and we are given the energies of these two photons, and we need to find the value of m. That what would be the value of m in this problem. So as always, this thing remains the same. I told you, I think in the very first class, that I have, that these are some pre-checks. It's very good. I keep on repeating them so that it becomes ingrained in your brain. If you do these three things, then you can blindly apply the formula that we had talked about. So inertial frames. So I should have drawn the frame here. So there is one frame here, S. Rest frame or lab frame. These are two synonyms which are used. So inertial frames, yes, because it's at S is at rest, so it is inertial. Moving frame, there are no moving frames because everything, all analysis is happening only in this frame, so this is not applicable. Number of dimensions, question is fairly clear. It's talking only x direction, so it's one dimensional picture, and fortunately it's talking about the positive x, and all our formulae are in x, right? So how to approach this problem? Again, so what we can do is we can approach it like conservation of momentum and then conservation of energy, right? So first I'll do the conservation of momentum. Again, the picture remains similar. So this is frame S. This is before picture. So this is our particle P. It's moving, let's say, with the velocity u. This is before. This is the after picture. This is after. Frame remains the same S, and here are two photons, gamma 1 and gamma 2. So what I'll try to do is I'll try to balance the momentum. Note now there are two directions. Notice this 45 degrees, so I should draw the coordinate system here first. This is x direction, this is the y direction. Okay, so let's just try to balance the momentum, right? Let's just try to balance the momentum. First of all, what is the momentum of before in x direction and y direction? Okay, so I'll assume that this velocity, it's given that it's moving in only in x direction, this particle, right? So I'll write the initial momentum here. So P initial, it's a vector, so it will be m times whatever the mass, so let's call this capital M. So note that this is the rest mass here, so let me denote it by m naught for the sake of, so that I don't confuse. This is the relativistic mass m times its velocity. In this case it's ux I cap. So initial momentum would be m ux I cap. Okay, let's talk about the final momentum, pf. So what's the pf? It will be p of gamma 1 plus p of gamma 2. Okay, so what's the so in the case of momentum, what happens is that we know in case of photon, we know E equal to pc. That's the energy of photon is equal to momentum of photons times the speed of light. So I can write the momentum of photon. So I should say photon momentum is equal to energy over speed of light, the energy of photon over speed of light. All right, so let's say it's this energy is E1 and this fellow has energy E2. So this will be okay. What I should do is that I should break in x and y direction first of all. So we know it's moving at speed c in this direction, right? So let's just try to break that down. Okay, so I'm just talking about c for gamma 1 here. So it will be c cos 45, c sin 45, right? So this comes out c by root 2, and this also comes out to be c by root 2. Similarly, this is 60 degrees. This is again c. This is c cos 60. C cos 60, I think it's c by 2. Yeah, this is c sin 60. This will be root 3 c by 2. So what I'll try to do, I'll try to write this expression in I cap and y, x and I cap and j cap. So first momentum would be this, the momentum, x momentum due to the first photon. So I can write it as okay, I think I'm doing something wrong. All right, let's go ahead. So this will be E photon over over c, and so whatever the momentum is there, it will be 1 by root 2 times I cap plus E photon E1. So I can write this E1, this is photon 1 we're talking about, E1 by c into 1 by root 2 j cap. So this is the momentum of first photon, and this would come out to be here. This would be E2 by c into 1 by 2 I cap minus E2 by C root 3 by 2 j cap. Negative sign is because this is in this direction, right? So I'll just now club the two terms, the I cap and j cap terms. So this will be E1 by C, E1 by root 2C plus E2 by 2C I cap plus E1 by root 2C minus E2 by C root 3 by 2 j cap. Okay, I think I'll not be able to solve this problem. We'll take it up in the next class, but the approach will be similar. We'll try to balance the momentum here, and then we'll try to balance the energy, and we'll try to find out the value of, because you notice that m is also unknown, m we need to find out, and ux is also unknown. So hence two equations, we need two variables. Two variables, we need two equations. First equation will come from the conservation of energy, and second equation will come from conservation of momentum, and using those two expressions we'll find out the value of ux and m. So yeah, so we'll do it in the next class. So
इसका y component cancel out हो जाना चाहिए ना?
yes, that's what I was going to say. We have time, so let's just try to see the y component. So Harish is saying that y component should cancel out because initial momentum was exclusively in x direction. We'll just confirm that. So that's a good point. So let's do that. So E1 by root 2c. So I'll just drop the c here, and I'll calculate E1 by root 2. So E1 is, I think that was 1, if I'm not wrong. Yeah, 1 giga electron volts. So this will be 1 by root 2. This will come out to be 0.707. And E2 into root 3 by 2. E2 was 0.82. So this is 0.82 into root 3 by 2. Let me get my calculator. So root 3 is 1.73 by 2 into 0.82. That's coming out to be 0.71 again. So this is also coming out to be 0.71. This is plus 0.71, this is minus 0.7. So this turns out to be 0, which actually makes sense because initial momentum was exclusively in x direction I cap. So what I can say finally is that mux should be equal to, so this expression, E1 by C root 2 plus E2 by 2. So we have got our first expression here, right? But we know E1, we know E2. Sorry, this is C also here, but we don't know. So both of them are unknown. So when we do the conservation of energy the next time, so how we'll do, I'll just summarize that. So the energy here would be, E initial would be gamma m naught. This is m naught. The rest mass I'm assuming m naught. Gamma m naught times C squared. The final energy here would be, E final would be E1 plus E2. Very simple. So this will come out to be 1.82 giga electron volts. If I equate these two, so it will be gamma m naught C squared equal to 1.82 GeV. This is the second expression, right? In the previous slide I had, so this was gamma m naught. M is gamma m naught. So first section was gamma m naught into U is some constant. So you can see gamma m naught, you can just cancel out gamma m naught, you calculate U, and then you can calculate m naught. We'll do it in the next class. I'll not hurry because it's good when you're doing a problem when I'm doing a problem for the first time, it's better not to hurry. So I'll pause here. If you have any doubts, comments, questions regarding this class specifically, first ask that, and secondly, if there are no comments regarding this class, then I'll still stay back, and then we can talk about some more for some previous doubts or some other things regarding special theory of relativity specifically. So I'll pause here, and yeah, you may ask your doubts now, if any.
Hello.
Yeah, Harish.
Sir, I have a doubt.
Yes.
Related to previous classes.
I'll request you to, Harish, I request you to wait for some minute. So if other people have no doubt regarding specific to this class, then we can talk about doubts regarding the previous classes. So let me just confirm. Does anyone have, if anyone has a doubt related to specifically the energy, momentum, kinetic energy, collision, decays. By the way, in the next class also we'll be doing decays. So these concepts will again get revised. But still, if you have some doubts, some comments, please speak up. Otherwise, we'll move to some doubts regarding the previous sessions. All right. ठीक है. So if any one of you has doubts regarding to previous sessions, um, now we'll discuss them. If anyone wants to leave, you're free to leave, but I'll be staying back to answer the doubts. So first, Harish, you are the first to speak. Go ahead regarding the doubts about previous sessions.
सर ओके सर. सर मैंने आपको कुछ क्वेश्चन सेंड किए थे आज.
Yes, we'll be talking about it. I'll do a couple of them maybe. Um, any other thing?
यस सर. सर आप पहले बोर्ड पे आइए, मतलब स्क्रीन पे.
Screen should be visible. Is it not?
नोट्स. यस सर. यस सर. सर आप क्या कीजिए, एक्स एक्सिस और वाई एक्सिस ड्रॉ कीजिए.
Okay, Harish is asking me to draw an x-axis and y-axis. Hold on. I have drawn an x-axis. I have drawn an y-axis. Yeah.
यस सर. सर तो दो फोटोन है, वो एक फोटोन तो एक्स दिशा में मूव कर रहा है और दूसरा फोटोन वाई दिशा में मूव कर
This
रहा
was
है.
a question that you had. What I am saying is that I saw those questions. If you have any other doubts regarding to some concept or other thing, I'll discuss this question. I'm not saying I'm not discussing that. If you have any doubt regarding to any concept or some other detail or some other comment you want to make, I'll go to the question. This is a question that you're talking about. I'll go to that question. But if you have any other comments, then please speak that regarding conceptual doubts. That was my
तो सर,
okay.
तो सर ऐसा कोई डाउट नहीं है आपकी.
Okay. So I'll get to Harish's question in a minute or two. But first, I must ask other people if you have any doubts regarding some previous sessions related to STR, Special Theory of Relativity. Just to be clear, in the next class also we'll be discussing Special Theory of Relativity. I forgot to share my email address earlier, so I'm sorry about it. So this is my email address and the YouTube channel name where I upload all these sessions that we discuss in here, and previous 12 sessions which were on electronics and semiconductors, BJTs, FETs, op-amps, digital electronics, and some current KVL, KCL. You can view, if you wish, you can go through just like this classes, they are there. So yeah, that's that. So if there are no other further questions on STR, then I'll guess no other questions on STR, Special Theory of Relativity. Then I'll move to Harish's question. This is a doubt which he sent me over email, so that's why I asked. 2 or 3 people have sent me some questions in the last week. I think I've answered. I tried to answer them, a couple of them. If not, get back to me. Now I'll get back to, if there are no other comments, then I'll get back to Harish's question. So this was the question. Harish, we had solved this kind of problem in one of the earlier classes also, but so I'll do it again. So 2 photons are shown. Is my screen visible?
Yes sir.
Okay. So in this question it says two photons are moving in the as shown in figure. So this is our S frame, a rest frame, and there are 2 photons. You can see this photon 2 is moving in positive x direction. Now we know the speed would be c, so I write this as ux2. Note the notation: u denotes velocity, x because you're talking in x direction, 2 denotes the second particle, should be equal to c. Let me write the direction also, I cap. Similarly here this should be uy2, u direction is y, sorry, uy1, the particle name is 1, equal to c. Photon will travel at c, and here the direction is j cap. But it's also imperative in this nomenclature here, y. So what we need to find the velocity of 1 with respect to 2. Okay, so we need to find the velocity of 1 with respect to, this means now we have to go in a frame of reference of 2. Okay, so we need to go in the frame of reference of 2. This means that this frame, S prime frame, or you can say it photon 2 frame of reference, or S prime for a simple nomenclature, this will be moving at a speed c in positive x direction, because that's the frame of this photon was moving at speed c in positive x direction. Now what will the picture in this frame? In this picture, this photon 2 will be at rest, because we are in the frame of reference of photon 2. Photon 1 will be traveling, right? What I'll do is that I'll assume photon 1 is traveling in x direction, ux1 prime. Notation: u denotes velocity, x denotes the direction, 1 denotes the particle. So this is the particle 1. Similarly, I'll take another velocity u y1 prime. U denotes velocity, y denotes the direction, 1 denotes the particle name, prime denotes we are in S prime frame. We need to find the velocity of 1 with respect to 2. This means we need to find u1 y prime and ux1 prime. I repeat, velocity of 1 with respect to 2. This implies uy1 prime we need to find, and ux1 prime we need to find these two velocities, right? So that's a problem, and we know the uy1 is cj prime, and also it's hidden the information that ux1 is 0, because this particle is only moving in y direction, so x component of velocity would be 0, and we are ignoring the z direction, so you can just ignore this formula, right? So what will be uy1 prime? Let's look at this formula. What I'll do is that I'll put 1 everywhere. I'll replace y by y1, this will remain the same, right? So now let's just put in the values here. So uy1 prime would be equal to uy1 divided by gamma 1 minus ux v by c square. ux1, we are talking about ux1 here, particle 1, so everything would be 1 here. What's the value of uy1? uy1 is cj cap divided by 1 minus, what is the value of ux1? ux1 is nothing but 0 times, what's the value of v? Value of v is c. This, we denoted v as the velocity of S prime frame. That's a nomenclature in this formula. This will be c over c square. This will come out to be c by gamma j cap. We don't know gamma, but we can calculate gamma. So gamma would be, hello, yeah, we'll calculate gamma in, yeah,
Sir, will you post this in the YouTube channel?
I will, that's what I told you.
Even this doubt section.
I post the complete video. Even when I do mistakes, I post even that.
No. Okay.
So you can, that's what I told you.
I have.
That's what.
I'm leaving.
Yeah, please. You can visit the video. I think I will upload it around maybe 10 p.m. or something, but it will be uploaded in a day or two for sure. Please go ahead. If any other people want to leave, you may leave. I'll upload this including this doubt to the YouTube channel. Right. So ux1 prime I can find, replace everything by 1. Okay. So this will be ux1 minus v 1 minus ux1 v over c squared. ux1 is 0 minus the value of v is c divided by 1 minus 0 times c over c square. So this is coming out to be minus c. Now if you know the value of gamma for a photon is infinity, this will come out to be actually 0. How do I know that gamma is infinity? There are two ways of knowing it. So first, and a more intuitive way I'll tell you is, you see, let's say there is a particle of mass m, it's at rest, so its mass is m naught. We know that when it starts to move, so this is rest mass. I'll use the other slide. So there is a particle at rest, so this is rest mass. So when this particle starts to move with some velocity u, let's say, it's called relativistic mass. We know that, and we know m is equal to gamma times m naught, right? So what's happening is that, and gamma an entity 1 minus v square over c square, where v is the relative velocity with respect to the frame. We know that this thing this velocity will always be greater than 1. For photons, when v equals to c, so this will become 1 minus c square over c square. 1 minus 1. 1 minus 1 is 0. So 1 over 0 becomes infinity. So gamma approaches infinity for photons. If you replace the same thing here, that's why I told. So what's going to happen is uy1 prime is coming out to be 0 j cap. So I'll say, so this comes out to be 0 j cap, this comes out to be minus c I cap. So the final velocity would be minus c I cap. So I can say u prime would be ux1 prime I cap plus uy1 prime j cap. This is minus c I cap plus 0 j cap. This is minus c I cap. Option C. We had done, I remember someone asked, if I'm forgetting the name, sorry, but someone had asked this very specific problem. Not in this case, they were moving in opposite direction, plus x and minus x. And we calculated, the answer comes out to be C. Because photon, if you remember in very first slide I said that the speed of light, this means the speed of photon will always be c in whichever frame you are. So what that means is that option A and option B are automatically eliminated, because here the magnitude would be root 2c. You cannot go about speed of light. This is again root 2c. So these two options are eliminated. These two may be doubtful, but since we are sitting on this second photon, so everything will, if you're sitting here, everything will appear as if it's moving back at minus c. So that's the doubt that Harish had. This is a very similar problem. Again, you just need to put in the formula that's shown here, right? Sorry, this it got so 2c by 5 and 3c by 5. So this is the S frame. These are particle 1, particle 2. Velocity of 2 with respect to 1. So this is S prime frame. So now we need to go at the frame 1. So we can say it particle 1 frame. Particle 1 frame of reference. So this speed would be 2c by 5. And you need to find the velocity of ux2 prime. Right? So you can just put 2 here, 2 here and 2 here. And you can calculate the value 3c by 5 minus 2c by 5 over 1 minus whatever 2c by 5 into 3c by 5 into 1 over c square. I think the answer would be, I think 5c by 19 minus 5c. One of these is the option. Yeah, so it will be c by 5. This will be 19. 15 minus 6 is 19 by 25. Yeah, so 5c by 19. So this would be the option here. In the previous question, velocity of approach as seen by observer on ground. So when you're sitting on ground, so what you will see is that velocity of 2 with respect to 1. So this is very simple. In this, for problem 5, so we need to find the velocity.
हेलो
yeah.
सर, इसका स्टेटमेंट समझ में नहीं आया. वेलोसिटी ऑफ अप्रोच का क्या मतलब हुआ सर?
Okay, so Harish is asking what do we mean by this term velocity of approach? So velocity of approach is nothing but relative velocity. You can understand it like this. Let's say you're sitting in a bus and you're moving, right? And you see another bus coming in front of you. So that's called velocity of approach. But for a person who's standing on ground, what they'll measure is relative velocity. So velocity of approach is nothing but another synonym, you can say, of relative velocity. Okay, so velocity of approach is nothing but velocity of 2 with respect to 1. But this time we are in S frame. Right, so I'll write velocity of 2 with respect to s minus velocity of 1 with respect to s. This is a very simple thing that we did in high school physics. How to find the relative velocity? You subtract the velocities. These are vector quantities, mind you, so direction matters. And s is the rest frame that we have. So this will come out to be v2s is 3c by 5 I cap. v1s is velocity of object 1 with respect to s, which is 2c by 5. 2c by 5, direction is I cap. So this will come out to be c by 5 I cap. In this case, the option would be this. That's a good doubt actually. Velocity of approach is nothing but relative velocity. But here the observer is on ground, so everything has to be in S frame. That's why I wrote like this. So yeah, that's that. Okay, I'm done from my side for today. Let's again I'll ask for you. You have any conceptual doubts or any doubt in the problem that we had discussed? Again reiterate, next week will hopefully be the last week for special theory of relativity. Thereafter I'll do some classical mechanics problem, and I have some quantum mechanics also, like putting particle in a well kind of problems. So I'll do them too. 1 second. Yeah, welcome Amit. um, Harish, just 1 second. So next week will also be special theory of relativity. Hopefully, last class we'll discuss some like particle physics, like protons and pions, and we'll see that how the physics, the relativistic kinematics there can be explained using special theory of relativity. So we'll see to that. Um, so yeah, that's it. If you have no comments or questions, you may leave. Thank you for your time. Thank you for your patience. Yeah, Harish.
सर इसमें वेलोसिटी ऑफ अप्रोच है, इसमें चाहे मैं इलेक्ट्रॉन 1 के रेस्पेक्ट में 2 का निकालूं या 2 के रेस्पेक्ट में 1 का, एक ही बात है ना सर?
No, it's different. So what Harish is asking is that direction matters. Relative velocity, direction matters. Velocities are
but magnitude will be same.
Magnitude will be same, yeah, but the direction will come out to be opposite. Okay, because in the first question it was asked velocity of 2. In this case, fortunately, there is no option called minus c by 5. Okay, but
Yes.
so here velocity of approach is here what they're essentially taking is a magnitude of the relative velocity. But for a complete picture, right, for a complete picture you must also have the direction also. Just keep in mind the direction also, because in some problems they'll give us sign also, and then we'll be in trouble.
Yes, yes, yes.
Okay.
सर जो मतलब मैंने आपको जो प्रॉब्लम्स भेजी है उसके मतलब सॉल्यूशन दोगे क्या आप मुझे?
I cannot do that. See, I can discuss it. There are, I don't know, 16 problems. I have discussed 3 today. I have done 1 in class. So I have done 4. Unfortunately I cannot see. If you have some specific doubt, you have to be specific. I cannot I cannot solve the problems like 16 problems.
I don't need the entire solution, but I need of just how to approach this type of question.
So
Just
how to approach
that
this type of
point I
question?
want to do.
That's what I'm
Yes,
doing.
sir.
That's what I'm doing in class. See, I don't just. That's what my approach is. Why? So I'll just tell you why. What do I mean? Just hold on a second. Yeah. Just 1 second. I'll tell you what do I mean when I say. So on your screen, this was the problem that we'll discuss in the next class. But you see this thing, the pre-checks that I'm doing here. This is the approach. This is the approach. This is my approach. I only have one approach. I do these 3 checks. I draw the diagram S prime, S prime. That's my approach. In every problem that I have discussed in today's session or 4 previous sessions, my approach has been exactly the same. I do these pre-checks. I draw the frame S. I draw the frame S prime. I write the velocities ux, ux prime, uy prime, or in earlier classes we saw x prime, x, t prime, t, and just solve the problem. That is my approach, and I'm repeating the approach over and over again. The question may change. The question can say anything. Today we discuss one question on collision and a question which is directly opposite to that of decay. But the problems were same in the reverse direction. That's it. The direction was reversed. But my approach did not change. So even if you show me any number of questions, even in the questions that your doubts, these 2 doubts, my approach remained the same. I talked about frame S here, frame S prime here. I use this formula. I don't know any other approach. That is the only approach I have. If you solve the problem, if you are stuck somewhere, I can help you offline. Okay, but I cannot give you the solutions for 16 problems. I'm sorry, I cannot do that. Today I discussed these in class because we had some time. So that's all.
Yes, sir.
Okay.
सर नेक्स्ट क्लास में एक क्वेश्चन मेसन डिके से रिलेटेड होना चाहिए, मतलब मेसन डिके से रिलेटेड क्वेश्चन
Why?
मैंने
Okay.
PYQs में देखा.
Okay. Harish is saying in the next class there must be a question on meson decay. Okay, my counter question is, what's so special about meson decay? Hello, Harish.
Sir, I am really confused whenever I see this type of question.
Now, today we discussed one question of decay, right? Where one mass was decaying into.
I will try this approach. Okay, from my side.
In the next class again we'll try this question. We could not finish this question where mass is decaying into photons, right? In the next class I'll do 2 questions from particle physics, in which one is a proton antiproton problem, second is a pion decay. Okay, That's what I'm saying. The way I'm choosing questions is to cover the entire spectrum. We started from the very basic in the very first class of space-time interval, which is the core of special theory of relativity. And from then we'll end in the next session to the particle physics, which is one of the important applications for this field. You'll see that you attempt your questions. If you're not able to solve it,
Yes,
drop
sir.
an email. That goes for other people also.
Thank you, sir.
Yeah, you're welcome. All right. So I guess we are done. Nidhi, Harish, Shangir, and Naveen. If you have any comments, otherwise we may leave. I'm closing the session. Thank you for your patience, staying back so long. If you have no comments, then I'll close this session. Thank you for your time, everyone.
Thank you, sir.
You're welcome.